also known as a slow response action potential. Now, you might be used to neurons or skeletal muscle cells that just sit there with a stable resting potential waiting for a signal. Not these guys. These cells are, well, they're leaky. They don't have a stable resting state. They're constantly, slowly drifting toward their firing threshold.
Okay, let's walk through the action potential. It all starts with phase 4, the pre-potential. This slow upward drift is caused by a slow leak of sodium through some very special channels. We actually call them funny current channels. As the cell drifts up to about minus 40 millivolts, boom, we hit threshold and enter phase 0. Now, instead of a fast sodium rush, L-type calcium channels open, causing a slower depolarization upstroke. Finally, in phase 3, the calcium channels close, potassium channels open, potassium rushes out, and the cell resets, ready to start that slow, leaky drift all over again.
So once the SA node fires, that signal can't just spread out randomly. No, it has to follow a very precise pathway that has a crucial built-in pause. This is all about engineering perfect timing for the most efficient pump possible.
So check this out. The impulse fires from the SA node and zips across the atria pretty quickly, causing them to contract. But then it hits the next major hub in the network, the atrioventricular, or AV node. And here, something really important happens. This signal gets held up. It's intentionally delayed for about 1/10 of a second. It's a tiny pause in the grand scheme of things, but it is absolutely vital.
And this is the key takeaway. That delay isn't a bug in the system, it's a critical design feature. That pause is just long enough to let the atria finish their squeeze to push all of their blood down into the ventricles before the ventricles get the signal to contract. It ensures the heart works as a perfect two-stage pump, maximizing how much blood gets sent out with every beat.
Okay, so after that critical pause, the signal is finally unleashed into the lower chambers of the heart, the ventricles, and this triggers the main event, the powerful contraction that pumps blood out to your lungs and the rest of your body.
This signal delivery system is like an electrical superhighway. After the AV node, the signal shoots down the bundle of His. It splits into the right and left bundle branches, which run down the septum, and then it fans out through this incredible network called the Purkinje fibers. Now, you've got to think of these fibers as the autobahn of the heart. They are huge cells that conduct the impulse incredibly fast, making sure the entire ventricle contracts at almost the exact same time for a powerful, unified squeeze.
Now, these ventricular muscle cells have a totally different job than the pacemaker cells, right? Their job is to contract, and contract hard, so it makes sense that they have a very different type of action potential. We call it a fast response potential. Unlike the SA node, these cells have a stable resting potential. They wait to be told when to fire, and their most famous feature is a long, distinctive plateau phase.
Let's walk through these 5 phases. Phase 0 is an explosive, rapid depolarization caused by a massive influx of sodium through fast channels. After a brief little dip in phase 1, we hit the all-important phase 2, the plateau. Here's what's happening. Calcium is flowing into the cell while potassium is flowing out. They kind of balance each other, which holds the cell in a depolarized state. This prolongs the contraction, gives it its power, and, this is critical, creates a long refractory period that prevents the heart from going into tetanus. Then, finally, phase 3 is repolarization, and we return to the stable resting state of phase 4.
So putting them side by side, the differences just pop right out, don't they? The pacemaker potential is all about automaticity. It's got that unstable resting potential and a slow, calcium-driven depolarization. The contractile potential is all about power. It's got a stable resting state, a super-fast sodium-driven depolarization, and that crucial plateau phase that allows for a really strong squeeze. 2 different jobs, 2 perfectly designed action potentials. This table is a fantastic summary for your notes. Just remember the sequence of the main players. Fast sodium in for depolarization, calcium in for the plateau, and potassium out for repolarization. And, really understanding which ion moves during each phase is absolutely key because this is exactly how many antiarrhythmic drugs work